in order to properly set up the integral, we need to first of all refresh our memory on a couple of physics facts. So first of all, we need to refresh our mind, our memory on the fact, hey, get out of my pool there. What are you doing? On the fact that fluid pressure depends on a number of basic things. This is a fact that is old hat for all scientists. In fact, if you remember, this is what good old Archimedes was thinking about when he found out the solution to the problem, jumped out of his bathtub naked and ran through Athens naked to let the king know that he had found the solution to his problem. I hope you are not going to do the same thing once you find out how to construct these integrals. So this fluid pressure depends on a number of things. What are these things? Well, it turns out that the pressure at any point inside the liquid is going to be equal to the product of rho times g times h. And you might wonder, who on earth are they? All right, rho is actually the density of the liquid, so it's a property of the liquid. For our applications, we're going to assume most of the times that this density is actually constant. You may run into some exercises where this assumption is abandoned and we assume that the density itself is going to change, but again, for now we're going to assume that it is constant, and in fact it does not really affect our construction to any extent. The second one, g, is the usual gravity. Of course, the pressure is going to be greater on Earth than is going to be on the moon. And if you go to Jupiter, you know that you're going to be subject to an awful lot of pressure if you immerse yourself into a similar liquid. And finally, H stands for depth. I'm using H instead of D to avoid problems with having differentials, which are also denoted by D, etc., etc. But as any scuba diver will tell you, the pressure that you feel underwater gets bigger and bigger as you go deeper and deeper. And therefore the pressure is going to be given by the product of these three. Now you notice that again, even though the density and the gravity may be assumed to be constant in many applications, but depth is definitely going to change, and something else in our application is going to change, and that's why we're going to require an integral. What is going to change? Well, what we're interested in is not really the pressure. The equation you have in front of you is everything you need in order to study the pressure. What we want to know is the force, the total force that is being exerted on this object that we have immersed in water. And again, by definition from physics, the force is going to be equal to the pressure times the area, right? And so the pressure is going to be equal to rho times g times h. The area is equal to a, and so we have this nice looking formula. Great, as long as h is constant, which even in the situation you have in front of you it is not, and as long as the area is constant, or it's the same at every level, and as you can see from this picture, it is not. I mean, as we go down through our object from the surface of the water down towards the bottom, the width of this section of this object changes. So there are a couple of things which are changing. So we're required once again to use the good old slice, approximate, add up, and take the limit method. So let's do it. So first of all, we're going to slice this region. So how are we going to do that? Well, we're going to consider a whole bunch of horizontal slices, because of course the variability comes from the depth, and therefore as we go from the surface down towards the bottom, we're going to consider different slices. So let's say at this depth h, we're going to consider the corresponding slice. So it's a slice of our object which is going to have a width of w, say, and of course in a specific application we'll have to know what w is or have some function for it. And how thick is the slice? Well, of course, delta h, right? So that's the usual notation that we're going to use. So for this particular slice, a good approximation for the force which is exerted by the fluid on that object along that slice only is going to be that the force is approximately going to be equal to rho gha, which in this case is rho ghw delta h. You want to stop and pause and think for a minute about that. All I'm doing is I'm using the general equation for the force, rho gh, and instead of a, I'm using the area of that rectangle, which I'm using to approximate the real slice. Notice that the real slice actually has slanted sides and actually even curved sides. So this is an approximation. As usual, once we take the limit, that approximation will go away. All right, so how we're going to compute now the total force? Well, we're going to take all of these pieces, rho g h w delta h, and now we're going to have, as usual, to add them all up. So that will create a sum from 1 to n, and finally take the limit, which will make, of course, a limit as n goes to infinity of the sum from 1 to n of rho g h w delta h. Good old integral. Again, it's the definition of Riemann integral. So this is going to be equal to the integral from a to b of something that will look like rho g h w dh. The only change we have made is just delta h will change to dh. Now notice that the way I've written it down, the way that comes up from our construction, everything is inside the integral. But as I said, in many applied situations, in many of the applications we're going to deal with, rho, the density of the liquid, is assumed to be constant. So in fact, we can take that one outside of the integral. Also, for many of the applications we have in mind, we're going to look at bodies of water or liquid which are fairly small with respect to the Earth's radius, and so gravity is not going to change much, so we can move gravity out of the integral. In some situations that's not going to be true, in which case you may have to move the integral, the quantity is still inside, either rho or g or both of them. How about h and w? Well, h is the variable, so we cannot take that one out. W, it depends on the object. Sometimes it's going to be constant, sometimes it's going to be changing as the depth changes. And so in each case, you'll have to figure out what is the width of each of those slices at each particular depth. So this again will have to be done case by case, and also what A and B are will depend on case by case situation. You'll have to figure it out in each case separately.